Hello, everyone, and welcome back. 814, talking about revolution still, about horizontal and vertical lines, and I have two examples here that we're going to work through. Now, before we talk about that, just before I look at this, for example, let's just do a quick recall up here. And that's that we've talked about two ways to calculate volumes of revolution. Volumes of revolution. And one is to use cylindrical discs. And the other one is to use cylindrical washers. And the idea there is that disk, where you have the integral, which would add it all up, add up each of the volumes, that is, of each cross section. And then the cross sections, being cylindrical disks, are really just like cylinders. So it comes from pi r squared times h, but the h ends up becoming dx. Now, cylindrical washers is the more general case. In fact, this is a version of washers, where washers, just because the washer, the idea is it's an open hole there. So that's a washer. A disc is a closed cylinder. Okay. And a washer is the idea that it's pi of the outside. So it'd be pi r squared dx minus the volume of the inside, which would be minus pi little r squared dx. But we can simplify this into just saying volume is the integral of pi, the outer radius minus the inner radius squared, and then the thickness. Okay. So that's the idea of what we've learned so far. And I know it's kind of tiny. I hope you can read that. But again, that's pi r squared, where dx is the height or the thickness of each cylinder. And then same thing here. The big R is your outer radius. Little r is your inner radius. And your dx, again, is the thickness of each cylindrical washer. Okay. So there it is, a little recap. I hope you can kind of follow that. I hope it wasn't too blurry and too small, but something small. Now, let's look at this example. For the boundary region between y equals 1/3 x and y equals root x, we're going to rotate it two ways, about the x-axis and about the y-axis. So let's make a pretty accurate graph of this. And I know, let's see, make it pretty big here. And the reason I want to make it big is I'm trying to make it accurate if possible. So we know that 1/3 x would be up 1 over 1, 2, 3, up 1 over 1, 2, 3, up 1 over 1, 2, 3, where that's the 0.93. Okay. And then root x, knowing that you have a point at 1, 1, 2, or 4, 2, 1, 2, 3, 4, up 2. And then your last one would be 9, 3 as well. So there's 1/3 x, and there is root x. And we're talking about this region right here. Now, if we rotate about the x-axis, so I'll do the x-axis in pen, and then I'll do that second problem there in my green marker. Not if you can actually tell the difference. Doesn't look like you can. I apologize. All right, first one, x-axis. So here's your x-axis, and we're going to rotate it about this way. So if I consider the shape I'm going to get is if I draw a rectangle to represent the area between the two curves, and I rotate it about, what I'll end up getting here is I'm going to end up getting a washer because of the hole. So if we set it up, so A, it's going to be your volume is going to equal pi, and we'll figure out the bounds. Well, the bound is going to be from 0 to 9 of each shape. Now let's draw the cross section so we understand what we're looking at here. So we're looking at a washer where I'll have it out here. Your outer radius, r, is going to equal, so your outer radius is the distance from the outside curve all the way down to the center, which is just your function root x. So your outer radius is root x. Your inner radius, which is from your inside to the middle of that shape. So your inner radius is from here to here. I'm trying to make it bold so you can see it. Well, that's just your distance from 0 to your function 1/3 x. So your inner radius, your little r, is 1/3 x. So knowing our formula, it's going to be volume is going to be from 0 to 9. We're going to add up all of these washers. So again, the integral, which is the s sign, adds up all these integrals, and the volume of this washer is going to be pi of outer radius squared minus the inner radius squared times the thickness of each one, which is dx. So I guess if I make this 3D, it's important to have this picture. The thickness here is dx, as these are very small widths along the x-axis. So plugging in what I have now, it's going to be volume is equal to 0 to 9 of pi, your outer radius, which was root x squared, minus your inner radius, which is 1/3 x squared. And I'll put that in parentheses so I make sure I square that correctly, dx. All right, and we're going to work through it by hand. Pull out the pi, because that's just a constant. And you get 0 to 9. Root x squared is just x minus, and this will give me 1/9 x squared dx. The integral of that is going to be pi, and my integral, the antiderivative is going to be x squared over 2 minus, well, then you get x to the third over 3, and that 3 and 9 will make that 27. And we're valuing from 0 to 9. All right, so then we end up getting here, volume is going to equal pi. If I plug 9 in, I'll get 81 over 2 minus 9 to the third. I don't know what 9 to the third is, 200 something. 729, so minus 729 over 27, and then all of that will be minus 0 if you plug that in. And I guess going farther, trying to keep this exact, let's see, 81 times 27, we'll end up getting pi 2,187 over 54, multiplying each of these by 27, minus, and then 729 times 2, minus 1,458 over 54, and subtracting those, your exact area under the curve is 729 over 54, which I don't think that simplifies. Yeah, it doesn't, so units cubed. So there's the volume about the x-axis, which approximately, what is that, 729 over 54 times pi is about 42.412 units cubed. And if I wanted to check my math, because I know I did it by hand here, hopefully I did it right. Let's see. Integral from 0 to 9 of pi, well, I'm going to put the pi in front here, seeing it's just a constant, of the outer radius squared, which is root x, and all of this was squared, minus your inner radius squared, which was 1/3. I'm going to put parentheses around 1/3 there, 1/3 x, and all of that is squared. So that's your outer radius squared minus your inner radius squared dx. And hopefully I got this. Good, I did. Whew, I was hoping I didn't have to redo this video. All right, so there's your volume rotate about the x-axis. Now let's do about the y-axis, second part of this. All right, so rotating about the y-axis, where if we look at area under the curve about the y-axis here, we're going to have rectangles that look something like this. And rotating about the y-axis, well, what are you going to end up getting here is you're going to end up getting something that looks, you're going to get another washer like so. Okay. So if we calculate the volume of this washer, do it right here, B, well, let's see, let's draw this out. Where we have it drawn out, I'll draw it again right here. There's a 3D shape. So what's your outer radius squared? So your outer radius squared, your big R, is your distance from this curve, which is 1/3 x to 0. So y equals 1/3 x, but since we are changing with respect to y, we're going to have to get this in terms of y. So then that will become x equals 3y. So your outer radius is 3y. your inner radius from this part of the rectangle to 0 is the curve y equals root x to 0. And if I convert that in terms of y, I'll get x is equal to y squared. So your inner radius is y squared. Good. So if we set the volume, we're going to get the volume is going to equal, and in this case, we're going from 0 up to 3. That'll account for the accumulation of all the rectangles vertically between those two curves. And it's going to be pi times your outer radius squared, which is 3y, and all of that squared, minus your inner radius squared, which is y squared. So again, that's outer radius squared minus your inner radius squared times the thickness of that cylindrical washer, which in this case is going to be dy. Okay. Now, we can work this out by hand if we want to, but for purposes of saving time, I'm just going to put in the calculator and see what we get. And what you end up getting here is from 0 to 3 of, and again, I'm going to put the pi out in front, make it a little bit easier on me. Pi times 3x squared minus your inner radius squared, which is x squared, and that's squared. So outer radius squared minus your inner radius squared dx. And what we end up getting here is the volume of this curve is 101.788 units to the cubed. And you can see here, the idea is, does it matter which way you rotate? Well, absolutely, it matters which way you rotate. And just visually, when I drew this, the fact that this curve is more so moving away from 0, when we rotate about the y-axis, that's going to create a larger radii, which will account for a larger washer. Then when I rotate about the x-axis, these are smaller washers at most of these points. Okay. So there is a little bit more example, and that's using washers. Let's look at another example. Okay. So example 2, the last one we're going to do in this video, is a bounded region between y equals negative x squared plus 5 and y equals 0. So if I have my curve out here, plus 5, 1, 2, 3, 4, 5. Let's go a little bit higher. So there's 5. Negative x squared, which I don't know, just going to do a sketch for these purposes. Will look something like this. And y equals 0, which is the x-axis. Okay, so there's my bounded region here. And we want to rotate about the x-axis for the first part, so I'll do that in black again. So about the x-axis, that's going to come towards us and create a, if we do that part, we end up going to create something that's a, it's not an elliptical, it has a little bit more definition to it. Something that looks like this is a 3D shape. And that's a bad example there, but we get something like that. So if we rotate about the x-axis, let's look at our rectangles that would fill up the area under the curve. So if I drew a rectangle here, I'll just do left endpoint rectangle. Okay. And we rotate about the x-axis. Well, what do you end up getting? When you rotate about the x-axis, we're going to end up getting something that looks like a cylindrical disc. So if I draw it out here, so A, it'll look something like this if I rotate about the x-axis. Okay. Now, what's the radius of this? Well, notice what I end up getting for part A is this is a cylindrical disc. There's no hole in it. Okay. So the volume of a cylindrical disc is just a pi r squared h. So what's the radius? Well, the radius is from 0 up to my curve, and my curve is negative x squared plus 5. So my radius here is going to be negative x squared plus 5. And the height of these discs are going to be dx, that very small change in x as we make these rectangles and then rotate these rectangles around, creating these cylinders, cylindrical discs, that is. So if we use the volume here, it's going to be volume is equal to, now what are the bounds here and here? Now you could, of course, solve for it, right? We could do when does negative x squared plus 5 equal 0? And then you'll get here, when does x squared equal 5? Minus 5 divided by negative 1. And we'll get x is going to be plus or minus square root of 5, which will fill this in. But maybe you don't want to do it by hand, or you want to check with a calculator. So just as a reminder, you could do this on a calculator, find those bounds. So if you put the function in there, negative x squared plus 5, and then you use the calc feature, second calculate, the enter, in this case would be the 0. So what's my 0 over here on the left? Pick something to the right, guess in the middle. This 0 is at negative 2.236, which, by the way, is negative root 5. And then if I calculate my other 0, pick a left bound somewhere over here, right bound obviously has to be on the other side, guess in the middle, and you'll see that that's root 5 too, right? So again, that's 2.236, but if you don't believe me, square root of 5 is that number, okay? So we're doing the volume from negative root 5 to root 5, and it's going to be pi times your radius squared times your height of each disk. So again, that's adding it all up. So if we plug all that in, it's negative root 5 to root 5 pi. Your radius was negative x squared plus 5, and all of that's squared. And the height of this disk is dx. And if you put that in a calculator rather than work this out by hand, we'll end up getting here math, function integral, negative root 5 to root 5 of, I guess in this case, pi will be in it, pi, parentheses, negative x squared plus 5, and all of that is squared. So it's pi r squared times dx. And what we end up getting here is 187.328. 187.328 units cubed, approximately. Okay, and there's the volume of the diving. Now, something to know is I might have said earlier in the video, like I said, a washer is a general case where a disk is a special version of it. And the reason for that is the washer will account for the volume of anything. The disk is just the volume when the inner radius is 0. So notice if we were to do a washer method here, I'll just do it quickly over here. Well, the washer method, if I draw this out, your outer radius squared, your big R, is your negative x squared plus 5, which is what we had over here. And then your inner radius squared is 0 because there is no inner radius. So what ends up happening is if you use the washer method, you get negative root 5 to root 5 of pi, your outer radius squared, minus your inner radius squared, and then dx is still the height of each disk. And notice that this is the same as this. So that's the idea, is that really a disk is a specialized version of washers, cylindrical washers. Okay. Now let's do B. What if this volume is rotated about y equals negative 1? Okay. Now this one's going to be interesting. I'm going to draw a new picture here so we can see this. And it'll just be a sketch, of course. Okay. So y equals negative 1 is now down here. Okay. And we're still bounded by y equals 0. So remember, we are looking at this region here still. But now we're rotating about y equals negative 1. So let's think about this. What we're going to end up getting here is if I look at the area between these two curves and make a rectangle, okay, and I rotate this about y equals negative 1, well, what I'll end up getting here is I'll end up getting a washer. Okay, so if I draw it out here, it'll look something like this. Or outer. So I'm getting a washer. And the washers will fill this space up. So let's calculate our radius. So our outer radius, well, let's see, our outer radius, well, notice that in the past it's usually just a function, but now in this case, what's the radius from the outside all the way down to the middle of this washer? Well, notice that the distance from the curve to y equals 0, the distance from here to here is your function negative x squared plus 5. But now there's an additional distance of 1 that we created. So what's the outer radius where it's the curve to 0, so it's your negative x squared plus 5, but then we have to add on 1 to account for that larger radius there. So, we could simplify this, of course, and just say it's negative x squared plus 6. But it's important you see where that plus 1 comes from because the radius is slightly larger there. Now, what's your inner radius? Now, in the last problem, the inner radius was 0. Now, in this case, your inner radius is the distance from 0 to 1, which is just 1. So your inner radius is the distance from here to here, which is just 1. So I'll draw that here. Your inner radius here, r equals 1. So putting this together, we're going to have the volume is going to equal the integral from, and it's still this bounded region. So again, you are still going from negative root 5 to root 5. And since it's a washer, it's going to follow pi times your outer radius squared, which we got was negative x squared plus 6, minus your inner radius squared, which was just 1 here, times the thickness of all these, and I forgot to label, and that's going to be dx, as we're filling the space up in that curve. And there it is. So notice that sometimes with the washer, if it's not the x or y axis, we have to account for the radius changing a little bit. Okay. Now, we'll just put this in a calculator and see what we end up getting. Now, by the way, if we rotate this around, it would be an interesting shape. It almost creates a donut there, where you're going to get this shape, this part of the curve filling in all the way on the outside, leaving that inside space there. Pretty neat. Now, let me put this in so we can finish this problem and be done. Be from negative root 5 to root 5. And by the way, it should be bigger than this. All right, we created bigger washers. The volume should be getting larger. Hopefully it is. And it's going to be pi times your outer radius squared, which is negative x squared plus 6, minus your inner radius squared, which was 1 squared, dx. There you go. And hopefully that's larger, which it is. Your volume there is about 280.993 units cubed. And that's the volume of this shape that we created, which, again, I believe if you fill that out, you'll end up getting a donut of a way, which sounds pretty good, by the way. So there it is, a little bit more volume of washers, discs, and talking about sometimes when you have to account for that radius. Okay. Hope that helps. If you have any questions, do let me know. All right, bye-bye.